It's by Tom Donaldson from Stanford. He's going to talk about neologicism. And after the talk, we'll have a reception in the common room of the philosophy department on the 4th floor. So please join us so we can continue the discussion. There's going to be some free food and things like that. All right. Please.
Okay, thank you very much. I realized that the whole thing was planned rather at the last minute, so that coming to this talk is perhaps something of an inconvenience for many of you. So I'm very happy that you're here, and I hope that you find it worth your while. I decided that rather than presenting a sort of detailed research talk on some specific topic, that it would be more interesting for many of you if I gave you a more general picture of the kinds of the research project. So that's the sort of talk that it was, that it will be. Of course, if you want more detail on any particular point, then you should just push me in the Q&A period. Good. Okay, so to begin, I want to introduce to you a certain position in the philosophy of mathematics. It doesn't have a standard label. I have got used to calling it neologicism. So here is one statement of it. So this is A.J. Ayer from Language, Truth and Logic in 1936. The truths of pure mathematics are analytic, in the sense that each follows simply from the definition of the terms contained in it. And then again, similarly, this is Hempel on the Nature of Mathematical Truth, 1945. The statement that 3 + 2 = 5, then, is true for similar reasons as, say, the assertion that no sexagenarian is 45 years of age. Both are true simply by virtue of definitions or of similar stipulations which determine the meaning of the key terms involved. Statements of this kind share certain important characteristics. Their validation naturally requires no empirical evidence. They can be shown to be true by a mere analysis of the meaning attached to the terms which occur in them. And then again, one more. This is Reichenbach from the axiomatization of the theory of relativity. The axiomatic method has most frequently been applied in mathematics. It has become customary to reduce a controversy about the logical status of mathematics to a controversy about the logical status of the axioms. Nowadays, one can hardly speak of a controversy any longer. The problem of the logical status of the axioms of mathematics was solved by the discovery that they are definitions, that is, arbitrary stipulations. Now, I love this quote. I just love the bravado of this quotation. Reichenbach is completely convinced not only that he has the solution to the problems in the epistemology of mathematics, but also that it's beyond controversy because it's so clearly correct. Anyway, this is neologicism. So let me just have a go at paraphrasing what Reichenbach has in mind when he talks about the axiomatic method. So one begins simply with axioms, and these are true by stipulation. They're just definitions. So for example, one of your axioms might be that 0 is a number. Alternatively, it might be an axiom that if x is a number, then x plus naught is x. And Reichenbach's idea is that these things are true just by stipulation. We just declare by fiat that these things are going to be true. And if somebody challenges us, if somebody asks us to give some argument for the truth of these propositions, all we can say is, look, it's just part of what the words mean. That's just the end of it. I should briefly mention here one variation. Sometimes neologists think that the definitions should take the form of inference rules rather than statements. So instead of, for all x, if x is a number, then x plus naught equals x, we should have an inference rule saying that you can infer x plus naught is x from number x. That distinction turns out to matter quite a lot in various cases, but and we'll get to that later. Step 2. One then simply deduces theorems from the axioms. The theorems must be true because they're logical consequences of the definitions, which are true by stipulation. Now, there's one very obvious objection with this position, which we should deal with immediately, which is that mathematics doesn't always look like that. So one sort of case is historical mathematics. So if you pick up a book of analysis from the 18th century and go through it and try to divide the statements into, the ones that are definitions and the ones that are theorems, you will find it immensely difficult. So if you look, for example, at Cauchy's cours d'analyse, you'll find that he does label some statements axioms. At one point, I think, for example, he says that it's an axiom that addition is commutative. But the things that he lists as axioms aren't nearly strong enough to entail all the theorems. There are lots of extra assumptions being made in the proofs that he never writes down. So it becomes extremely difficult to distinguish the axioms from the axioms or the definitions from the other statements. And yet, I think that Cauchy knew that some of these theorems were true, but he didn't know it using Reichenbach's method, apparently. So mathematics doesn't always proceed in by Reichenbach's axiomatic method. Another sort of case, arguably, one can justify a mathematical belief, even a belief in pure mathematics, using non-deductive arguments. So one of my favorite examples of this is the claim that pi is a normal number. Many mathematicians think that pi is a normal number, but they believe it not because they've succeeded in proving it, but rather because they have non-deductive reasons for thinking that pi is normal. Simply they've checked a very large number of the digits. It looks normal for the first few million digits that computers have checked, and so probably it is normal. So again, that's mathematical knowledge that's achieved not using the axiomatic method. And finally, one can consider cases of diagrammatic reasoning in mathematics. So when Reichenbach talks about deduction, he means strict logical deduction. So he's thinking of a mathematical proof as a sequence of statements only. So Reichenbach was missing out certain forms of diagrammatic reasoning in mathematics. Okay, so I think that the neologicists should just immediately concede that these points are correct. Reichenbach is describing, one hopes, one route to mathematical knowledge, but not the only route. So I think if neologicism is to be an attractive view at all, the claim is not that Reichenbach's axiomatic method is the sole source of mathematical knowledge. It should rather be that it is one source of mathematical knowledge. Okay. But I think that even if our neologicism is only a modest form of neologicism, in that sense, it's still, I think, an attractive claim in epistemology because it gives us a plausible account of one route to mathematical knowledge, although, as I said, not the only route. Neologicism is also attractive in metaphysics, I think. So, if the neologicist is correct, then nominalism can be refuted quite straightforwardly with the observation that it's analytic, for example, that there are infinitely many prime numbers. And what's more, neologicism seems to undercut certain metaphysical questions, for example, questions about what the truth makers are for mathematical truths. So neologicists have tended to say, look, the truth of the theorems of pure mathematics is just guaranteed by the definitions of the mathematical words. That means the truth of these sentences can be explained entirely by appeal to the definitions of the words they contain, and so there's no need to posit extra-linguistic truth makers for the truths of mathematics. Okay, so for the last few years I've been working on a sustained re-examination of this position, which involves a number of different components. So the first question to think about is, what is meaning? So Hempel said, statements of pure mathematics can be shown to be true by a mere analysis of the meaning attached to the terms which occur in them. But one needs to ask, what is meaning there? What conception of meaning do we need in order to sustain a neologicist position in the philosophy of mathematics? This is especially important because these empiricists of the 20s and 30s who I've been talking about were writing before the birth of modern semantic theory. So they were not explicit about the underlying conception of meaning that they were working with. Next question. What does it take for a definition to be successful? So, Reichenbach's idea is that you can just write down some number of statements. These are your axioms or your definitions, and you just declare that they're going to be true.